I want to begin with just a thought before we get into the nitty-gritty, and that's that after a while, sometimes the energy just seems to run out. This is a statement I like to reflect on because it encompasses the day-to-day life of patients that have a rare genetic disorder known as congenital myasthenic syndrome. It's quite a mouthful. This syndrome essentially causes chronic muscle weakness and these acute transient periods where breathing itself can stop, and this can prove to be fatal. Unfortunately for patients with this disease, there are no known cures and treatments are extremely limited. So this is where my project comes in that we're one of the researchers in the world that's interested in looking at this disease and figuring out what goes wrong, what causes this disease. There's one protein of interest that we're interested in, this is known as choline acetyltransferase, otherwise known as CAT. And where we're interested is looking at how CAT can be altered in this disease. And there's one mutation in particular that we're interested in, and why is because it's located within this highly conserved region of the protein that could have a regulatory function. So this is where my project comes in. We hypothesize that this region that surrounds this disease mutation is critical for the activity of this protein. So we started my project off by altering this protein, changing that region, and looking at its activity. So one thing I did not mention is that this protein generates a chemical called acetylcholine that regulates nerve-to-muscle communication. So we looked at the production of acetylcholine, and we looked at how much protein is present when we mutate it. And we found in both cases, most surprisingly, both of those levels tanked. They went right down. Very surprising. And this seems to be a common trend amongst other mutations found in this disease. We also, for the first time, continued and looked at how this protein is recycled, and we found that CAT is regulated through a structure called the proteasome. Kind of think of it like a recycling depot, where it takes in garbage or unwanted, changed and altered proteins, breaks them down so that they can be reused. And we found that both the normal and the mutated form are recycled in this manner. So using this new information, what we're going to do is apply it back to disease and ask, is this a common feature in disease? This could also lead us to investigating novel avenues for treatment, as once again, the avenues are very limited for this disease. And then lastly, as shown on the far right, we're able now to translate that information to other diseases, such as Alzheimer's disease, to see once again if this essential pathway is altered. Thank you very much.